So now let's dive a little bit deeper in dynamical systems. For me, they're very general, and sometimes they're in time, and sometimes they're more general. The way they show up in science and engineering, thanks to Newton, Leibniz, and other 18th and 19th century people, they show up as state space times a one-dimensional parameter, which we colloquially call time. Now, when you solve these problems, you might redefine this thing to be something unrecognizable, but usually when we teach it, we call it time. And mentally, we always stuck in time. And these are spaghetti that stay within the space. So basically, a flow is a continuously parameterized trajectory at every point in state space, going to any time, staying within the state space. They have properties that they are maps which at zero time, no motion, act as identity. They don't change the point. If I go some time t prime x, and then from that point, because flow maps points into point, I feed it into my pocket calculator and go time t, I will end up at the sum of two times. What does that mean? It means that, no matter at what time I'm looking at the system, I'm using the same law. So this is a statement of invariance of our description for all times. It might seem obvious to you, but it's actually a very powerful constraint on what dynamical system you want to study. And the last thing is maybe a little awkwardly stated, but if I start at point x0 in state space, go time t, I'll end up at some point which is parameterized by where I started, which strand of spaghetti am I on, and how long did I go along that. For flows, you want this to be continuous almost every place. Continuous just means that I can take derivatives of this and look at the neighboring points by Taylor expansion or some things. So that's what we expect from flows. They should be invariant law, they should add up. And this is actually a statement of a group property. If you start someplace, go time t, and then continue, this thing means functional composition, but you take result of this function and apply it. It's the same thing as just using the same law as for the sum of these things. So that means this operation form a group. Two operations of the same form as the initial ones, so they form a group. There is a little delicate thing that often you're not allowed to go back. You can only march forward. That's called a semi-group. And the property that they just add up, so it doesn't matter in which order, how much time I go first time, second time, that makes them abelian after Norwegian mathematician of 19th century. So they have a nice group property, and you have to stick this semi. You'll see our simplest example, like looking at one-dimensional maps, which you'll do pretty soon. They don't have well-defined functional inverse. So if f to the minus t is not well-defined, dynamical system theory survives that offense. And that's what the flow is. So basically, it's some continuous transformation with one parameter. Now, there could be more symmetry. This is a statement that your law doesn't change in time, but if you're looking at partial differential equations, There could be other symmetries in the problem, and the flow might be fancier. There might be several times, but let's ignore this remark. Flow lends itself naturally, as all continuous groups do, to a formulation that's infinitesimal in time. So if I am at time t and I add a little time tau to it, I can think I'm at time t and apply my law just for a little bit. Then I can define a derivative with respect to parameter by subtracting these two guys, Taylor expansion, whatever, and taking limit t equals 0. And that will give me a function of the same dimensionality as the flow, which we'll call x dot, or time derivative, evaluated at the particular state space point. So that this has time in it doesn't matter. It just means that when I look at my state space, which I remember was filled with spaghetti, right? So my state space, every trajectory went around. I'm taking derivative locally. So there's a little vector field of 10 dimensions. And in simplest cases of our ordinary world, this is really a velocity. If x is the position in your room, two-dimensional, then this is really at what velocity you are moving. And that's at the point which happens to have labeled, but that's not essential. And we have given it name x dot for convenience, thanks to Leibniz, I think. So every spaghetti, as we follow it, at every point has one of these vector fields. Now, if I'm looking at two-dimensional world, I can just draw these vector fields someplace. Better pictures are in Chaos book or any other book or Mathematica, whatever. But basically, it says that the way you can specify a dynamical system is by giving a differential equation for the velocity. This is this bunch of vector fields. And then you can integrate it by going a little bit, measuring tangent, 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 and find a trajectory. So that's how you numerically do trajectory. The numerical work is unspeakably uninteresting often, so I will not discuss it in lectures, but you should form a Python brigade and do it right, because you cannot do anything without it. So we have now a notion of velocity, which is not necessarily our physical velocity, it's in the state space. So for example, if you're looking at a fluid, it's infinite dimensional state space, so these vectors are all infinite dimensional, but in a state space, it tells you how things change. In small thing, it's defined every place. It looks like blades of grass, so we call it field, velocity field. The Germans thought of it poetically, it's like a field of grass.